This video will show you how to set up a model in COMSOL for a transient line source in the middle of a disk. So this is part two of videos that show you about this problem. This video will show you some variations on the model that I showed you in the first video. Okay, so if we open up the global definitions, one thing we notice is this model has these three parameters that are labeled with names that sound like they're geometric aspects, and indeed they will be used to define the geometry of the problem. There are various different lengths, and I'll show you where those are used in just a second. So let's open up the model itself and just go down through the definitions. The variables, this is the analytical solution for the analytical equation for the Jacob solution, and here are some constants that we can import using a text file. This model uses this step function to turn the flow rate off, basically. So during the first part of the simulation, we'll have the well pumping, and then we'll turn it off and we'll see the system recover after the well is turned off. And we'll do that using this step function. The step goes from 1 to 0 at this particular time, and there's a transition interval of 10,000. It turns out this will be seconds. So we can plot this up, and this is what that step function looks like. So the geometry looks like this. It's a disk, and the well is there in the center of the disk. And let's see, we can blow it up. It's right there. And we can see it a little bit better if we go like that, and there's the well. And I set it up with these three nodes here. The aquifer itself is a cylinder of radius that's defined by this variable and thickness that's defined using that variable. And so to show you how that works, these are defined up here as these parameters that I showed you. And so we can change the aquifer thickness from 20 meters to 200 meters, and then if we go rebuild the geometry, we see a thicker aquifer. And if we go through and use that expression aquifer thickness wherever we have that dimension, then everything gets scaled accordingly. So we've got a polygon that's used for the well, and the Z value goes from 0 to aquifer thickness. So we should be able to go in there now that we've changed the aquifer thickness and take a look at and we can see that line source or sink right down in there. So that was elongated along with the thickness of the aquifer because of this variable. And we also see that there's this cylinder at the center of the a model that's around where the well will be, around this line, and this cylinder will be used to create a fine mesh right here in this part of the model, the center part of the model around the well, and then we can use a coarser mesh further out where we don't really need to have there won't be a lot of change in the pressure, so we can use a coarser mesh out there. Okay, so in the physics, this is similar to what we used before. One thing that's a bit different though is that when we define the well itself, we can go here to an edge condition, boundary condition, and what we used last time was a mass source for a line, but in this version of COMSOL we have something we can specify as a well per se. So that's what I did. And well, it looks like it's not here, so yeah, there it is. So I specified the well, and there's a well diameter that we can include, and then we can have it be a production well or injection well. It changes the sign, and we can specify the pressure or the hydraulic head, or in this case, the mass flow. So what we used in the previous model was the mass flow per unit length. So we could still use that, or we could just specify the mass flow per se. So that's Q, which is the volumetric flow times the density of the water. And then here's this step function, step down flow, which is this step function that I showed you just a minute ago, and you can see that it has this name called step down flow, which we're using here at this declaration of what the mass flow rate should be. So that's going to turn off the mass flow rate at that time. Okay, so the mesh that we're going to use, that's shown here, and in the past we just use a default mesh, but what I'm going to do this time is show you a couple different kinds of meshes. So the first one is going to use a tetrahedral mesh right here in the center, and then another one out here. And actually, let me just go and change this back to 20 meters thick. So what I've done here is to create a mesh that is, I put a tetrahedral mesh, and then I put this, see, put this right here, this size control, and then set this to 25. Oops. And when I do that, then I can create a mesh that looks like this in the center, and then for this one, which I have selected remaining, and the size is here, I use just the predefined size of coarser. So when I do that, I've got a mesh that looks like that. Okay, so this is a finer mesh in the interior, and then it's coarser out here. It doesn't really get all that coarse because so long as I use a tetrahedral mesh, the size of it is going to be controlled by the thickness of the layer here. Okay, but nevertheless, that gives us a bit of a better mesh than we had before, because we can put a finer mesh right here in the center, and we don't have to have the whole model use that fine mesh. But this is where the action is going to be. This is where the pressure will change the most. So we'll benefit by having a fine mesh in here, but we won't have to have a fine mesh everywhere, which would potentially slow the model down. Well, it will slow the model down. Okay, so this is the study, and one of the changes that I made here, if you go to the time dependent solver and right click and go to time stepping, so the default will be like that, and this is the steps taken by the solver. When it says free, what it means is that the solver will figure out how big the time step should be, and what it does is it makes the time step get bigger. If things aren't really changing very fast, then it'll make the time step get bigger so that the solution can go faster. This works okay, but sometimes it goes too fast and you get kind of a rough looking solution. In other cases, you have the model changes, the boundary conditions change. Like, for example, you turn off the well, and if not much is happening, then the model may be making some very big time steps out there, and then if you change the flow rate at the well, for example, it may overshoot that and cause some problems. So if we switch from free to intermediate, then This requires that the model, that the solver solves the model at each time that you specify here in the where you set up the times for the model to run. Okay, so that sometimes will help get you a better model, although it will take longer for the model to run if you do this. So there's the result, and we're showing here the hydraulic head, and I changed the sign here because we're plotting this as a drawdown. And here's the Jacob solution, and we can see this is the hydraulic head from the model, this is the Jacob solution, and they become essentially the same out here. And this is what happens when we turn the well off. The head drops, and let's see, we can take a look at that. And this is what it looks like in real time. This is the drawdown increasing, and then this is where we shut it off, and we get something that looks kind of similar, but a mirror, kind of a mirror image. Not exactly, but kind of similar. This is where the head recovers back to the initial conditions. Okay, so some other things that we have is we've got a cut point here, or a cut line. This is a 3D cut line right there, and that is set up to do a profile from x equals 0 to x equals to y equals 0 to 1,000 and z equals 10. So that looks like this. So it's going to be a profile along that line, and it's going to use the transient study right there, data set from the transient study. And this is what the heads or the drawdowns, this is what the heads look like, where the head is getting negative because the water level is dropping. The drawdowns would be the negative of that. Like that. And what you can see is that as the line sink, as the well is active, we have plots, these plots here. So we've got a curve like that propagates out as the well is active, and then when we shut off the well, the head right here at the well itself drops, and we get this set of curves. Okay, so they're all superimposed. We might want to look at fewer of them. So I guess one thing we could do is just look at just pick out some times. So there's plots from 3 different times. We could also, let's do this, do manual. So there are 50 different solutions, and we can say start at 1 and go to every 5 to 50. So there's every 5 solutions. So that's a little bit easier to visualize, and we might want to make those plots a little bit thicker. There we go. And we could also plot them on a log scale. Looks like that. So let me also show you a different style of mesh. What I just showed you was this mesh here, and this works okay, but this isn't really going to be the best way to mesh a thin layer. It's okay if we just are interested in how things change in this direction, but we might be interested in how things change through the thickness. And if we did that, then we would have to make some, if we look at the side of it, we essentially just have one element that goes across. Well, I guess there are 2. There are 2 elements, and they've got this triangular shape and cross section. They're tetrahedrons in 3D. a way that might be better is this kind of a mesh. This is, zoom out a little bit. So this is a triangular mesh here on the face, and then that triangle is swept through the thin layer. So I've got five layers right here, and it's like five triangles stacked one on top of another. So it's a different shape of mesh element. And let me show you how to make that. So what I did was to go here with a triangular, select this zone here, this surface, and make a triangular mesh. The triangular mesh is just on this surface. So there's what it looks like. And we might want to make it a little bit finer, so we could change that maximum element size. And there's what it looks like. And now we've got another triangular mesh out here. And so when I build that, that's what it looks like. And now you can see that these elements get to be quite large. Now we wouldn't want to do this if we were really interested in the details out here. But if we're not, if we're really interested in just what's happening right in here, then we don't really need to spend all our computational resources calculating what's going on out here, so we can use a much bigger mesh. And so this triangle is, this allows us to generate a much coarser mesh. I could change the size here, and let's see. There, it gets even coarser. And then I use a swept mesh. So this is really just meshing the surface. So let's see. If I build it up to here and look underneath, there's no mesh there. That's because this mesh is really just on the surface. This swept mesh will take this mesh that I see on this surface and sweep it through the volume. And so now I see it on the other side, and if I look at the edge, I see that there are five elements, and I get that from this distribution. Okay, so this is a very simple geometry, and the swept mesh is set up just by default, and it works pretty well. There are various various settings here that we may need for more complicated geometries if the default doesn't work right. Okay, so what I've got now is a model with two meshes. I go in here to my solution and go here to this node, and if I go here to the geometry, I can select which mesh I want to use.